for having me. It's always a pleasure to visit. So I'm going to be talking about quasi-ballistic regimes of high temperature transport, a problem that I've been interested in for the last few years. Let me just start off with the obligatory reminder of hydrodynamics. So the Gulf, formerly known as Mexico, consists of many, many particles, but its response to weak perturbation can be summed up in just 5 equations. And we expect a one-to-one correspondence between conservation laws and hydrodynamic equations. And the fact that this is true very generally means that traditionally we have not expected interesting hydrodynamics in solid-state systems, because if I take a generic lattice model, it only conserves energy, charge, spin, and by symmetry, these things are usually decoupled. So in the solid state, in a crystal system, we typically expect a handful of not very interesting diffusive conservation laws. But increasingly, as we probe closed quantum systems and their ideal Hamiltonian evolution, we're seeing much richer regimes of hydrodynamics, whether that's the integrable hydrodynamics you've heard about in this talk, or the chaotic hydrodynamics I'm going to talk about today. So what inspired this was actually this landmark experiment on the 2D chaotic Fermi-Hubbard model, where the Bakker group at Princeton initialized this charge density wave at an intermediate temperature and half filling. So you just expect normal diffusive relaxation of charge. This is a chaotic lattice model. But instead, they saw something a little bit different. So at the longest wavelengths, which is the red curve in the figure, they did indeed see just slow decay of the Fourier mode that they initialized. But at shorter wavelengths, they got this blue curve, which is an underdamped mode. And this is a little surprising if you expect that the hydrodynamics of the system should just be pure diffusion. Why is there this underdamped feature in there? And so a question is this hydrodynamics? Does this really fall under the purview of this textbook theory, where at leading order in the derivative expansion, we have this diffusion term? And so trying to understand this plot basically has led me on this multi-year and ongoing journey. So the original paper proposed this very simple phenomenological model for what was going on. So they said, okay, it looks diffusive with a slight ballistic correction. Maybe it's just a long-lived charge current. And this model, so you let the charge just follow a normal continuity equation, but then the current has its own hydrodynamic equation, which damps slowly. So at short times, this gives you ballistic wave-like propagation, and at long times, you recover normal diffusion. Well, I mean, that's the sound. That's the sound. This gamma d is speed of sound squared. It's coming from this model. So I'm saying it's underdamped because it has this ballistic transient. Yeah, exactly. So even the interpretation needs to be refined. But anyway, this was the picture in the paper, and they argue that it was a ballistic to diffusive crossover. But in agreement with Jacopo's question, there is no a priori reason to expect a ballistic wave here. I mean, there could be many things causing this oscillation, and we're not really sure what it is. So my question broadly is, how could we have predicted this without knowing the answer? So this means in particular that what people call memory matrix methods for me don't count, because you're putting in slow modes by hand, and I don't want to do that. I want the theory to tell me what the slow modes are. So we tried to enhance this effect in a toy model where we confirmed that we could at least enhance the effect in a 1D toy model, but I would say a global understanding is still work in progress. So anyway, this is the concrete motivation from high temperature chaotic fermions that got me interested. But a recent related phenomenon actually crops up in 1D. And this is the phenomenon of quasi-ballistic spin transport in power law interacting XXZ chains. So the Mirzejewski and collaborators looked at these long-range interacting models, and they found that even though for intermediate values of the power law here, between 2 and infinity, this model is chaotic, they still saw ballistic transport for very long times. So in the units of this Hamiltonian, these were lifetimes of 100 to 1000. And in modern day numerics, or even these ultra cold atom experiments, that is all you're going to see is that long ballistic transient. So it seems worth understanding, and it seems related, at least superficially, to the physics in the previous slide. We thought this would be an easier setting for understanding. And in particular, they found this locus of the optimal anisotropy as a function of the power law for seeing this transiently ballistic spin transport. So this seemed pretty curious to me, and the functional form of this delta star was also quite tantalizing. And is it real? Can we understand this? And that's what I'm going to be talking about. So any questions? Yeah. So this is all going to be at infinite temperature. So the entirety of this talk, yeah. Other questions? Okay, so how am I going to estimate this time scale? So you're never far from integrability in 1D, as we've heard, and this model is no exception. So there are two integrable points in this phase diagram, the Haldane-Shastri point when alpha equals 2 and delta equals 1, and the XX point, which is the limit of an infinitely rapidly decaying power law, and delta equals 0. And something that's very nice about this problem, and just one of these happy coincidences in life, is that these 2 points are non-interacting points. So the XX model is probably the one you're more familiar with. It's a free fermion gas. But the Haldane-Shastri model is also actually a non-interacting theory. I don't think it's, at a microscopic level, no one has ever quite understood why it is a free spin-on gas, even though it's clear from the spectrum, but it is a free spin-on gas. And so you have these two non-interacting limits, and the optimal anisotropy that Mirzaevsky and co found is interpolating somehow between them. Now, the reason this is not a trivial problem is everything in between is chaotic. And these generic values of alpha in the middle are not obviously weakly coupled. Because if I try to do weak coupling kinetic theory about either of the integrable points, they will get the other integrable point wildly wrong. So if I try to perturb about XX, Haldane-Shastri will look very chaotic. If I try to perturb about Haldane-Shastri, XX will look very chaotic. And that's why I think there are no standard methods that work well here. Yeah. Sorry? Yes. Yes, that's true, but the spin current wouldn't be exactly conserved. So that's the difference. So at any rate, yeah, so that's a good point. So their extrapolation is actually finding the XX model. And yes, so going back to the main point, so there is no standard theory that works in this bulk regime, and that's why we're going to try to tackle this regime of generic alpha that's far from both. Okay, so first let me say what a complete theory of this problem would look like. So the first studies of this problem have been purely numerical. No one's tried to tackle the theory. And they are suggestive of a ballistic to diffusive crossover, but ideally we would first prove that spin transport is not ballistic. And this sounds trivial, but if you really want to say that I'm crossing over from ballistic to diffusive dynamics, you have to be able to rule out cases like the XXZ model with delta non-zero, for which the current decays a little bit and then plateaus. So second, we would, of course, compute the Kubo formula to estimate the relaxation rate. The problem is that the Kubo formula is so hard to compute in generic cases that no one actually really does it analytically away from integrable limits. So I expect both of these to be analytically intractable for this chaotic model, which is why we need something simpler. So instead, I pursued a poor man's version of this argument, which was, instead of ruling out arbitrary quasi-local conservation laws, let's first just try to rule out two-body conservation laws. Just see how hard this is and whether, actually ruling out a Mazur bound would be feasible at all. Secondly, instead of focusing on the Kubo formula, we focused on this instantaneous relaxation rate. So some people view this as a short-time quantity. A common objection to this kind of reasoning is, well, this is just the rate of change of this current at time zero. But yeah.
Just to clarify, the T here, you are in equilibrium, and it's a time difference. It's not something that you do initially, look at what happens starting from the special condition.
No, so these are infinite temperature averages, and this T is just the T of Heisenberg evolution.
You're in equilibrium at infinite temperature.
Yeah.
The time difference.
There's no time difference,
But
so it's a single time. So it's not 0 and T, it's literally T and T. And so that's the objection. So some people view this as a short time quantity because you should take J0 times JT. But the reason I don't particularly care that it's a short time quantity from the Kubo viewpoint is that we're only interested in the transient. This is dynamics that's dominated by the transient, so to capture the transient, it makes sense to focus on transients. And minimizing this quantity has actually been pretty effective at generating slow modes in practice. So the first paper to do this was by Hughes and collaborators back in 2015. We did something similar for 1D fermionic chains recently, and similarly found we could make very long-lived and quasi-ballistic currents. A referee for one of these papers pointed out that this has antecedents in the literature. It used to be called the moment method, but these authors were trying to estimate the spin diffusion constant by doing this calculation. And we're not trying to do that. We're really interested in the short-time dynamics. Okay. So a very nice feature of this effective relaxation rate, at least for the problem that we're looking at, is that it knows about integrability in this setting. And this is pretty non-trivial. I'm not sure how generic it is, but it does work for this problem at hand. And the reason it works so beautifully is because the spin current actually vanishes exactly at the two integrable points. Because XX and Haldane-Shastri have this free particle interpretation, dj over dt equals 0. And this seems, okay, so we know the spin current is conserved. What's the big deal? It seems unremarkable until you try to derive this from, say, Boltzmann theory at one point or another. And the scalar quantity that contains this essential information that the spin current is conserved is the rate of dj over dt squared. And just from the viewpoint of Boltzmann, this is a six-body operator. So we're used to thinking of kinetic theory as truncating low-order correlation functions. Maybe you stop at second order or fourth order. This, to me, seems to be a case that maybe you should be going to higher orders if sixth order is needed to even capture the XX model or Haldane-Shastri from first principles. And by first principles, I mean you really take the hierarchy of spin-spin correlation functions of the system and try to deduce the universality class of the dynamics without putting any knowledge of integrability in. I think you would need to analyze these kinds of high-order correlations. Okay. So in the remainder of this talk, I'll set up the problem in full generality. So for the set of models I'm interested in, get an analytical prediction for this locus, and you can see that, at least qualitatively, it answers my curiosity about why they were seeing this result. You can really recover it from this very simple-minded reasoning. And finally, I'll present some initial rigorous results on deducing integrability from transport, by which I mean that the class of transport that you see can actually be used to tell you something about integrability. And these are initial results, but I think they give some sense of what you'd have to do to prove this so-called integrability transport conjecture in full generality. So to set this up, it's simplest to think of actually the whole class of spin chains. So this is an arbitrary inversion symmetric XXZ chain with long-range interactions. The only caveat for Alvise's question yesterday is I want to explicitly exclude superdiffusion. And so it turns out that decaying faster than 3/2 with the distance is sufficient to do that. I'll explain a little bit more why in a second. And importantly, also related to discussions that arose yesterday, the spin is always locally conserved, even if I have really long-range interactions, but the spin current may be non-local. And so a really quick argument says, okay, we know it's globally conserved by Noether's theorem, we expect a local conservation law, and then this sum rule over here will tell us what J is. But more precisely, I can just go to the level of the Heisenberg equations of motion and microscopically prove this continuity equation with this very non-local current. And with this assumption on how A decays, this thing is generally well enough behaved to work with. So what this means is we can just compute this relaxation rate pretty explicitly and simply. So we compute the rate of change of these current operators in full generality, and then we can extract the rate of change of the current squared and the current squared itself. It's actually convergence of these expressions is where this constraint on the power law decay comes in. So this super diffusive regime that Knapp et al. Observed turned out to coincide with J squared having an infinite norm. I mean, I think we still don't very precisely understand the super diffusive regime, but it's clear why we need to exclude it here. And so we get this nice explicit formula for the relaxation rate that we can now try to understand this physics with. And more generally, this suggests a systematic strategy for trying to enhance these kinds of effects. We minimize this relaxation rate over a whole space of Hamiltonians rather than looking at any particular Hamiltonian. And this helped us quite a lot, finding interesting models in the fermionic case. Any questions? Okay. So having set up the formalism, let me first tackle the problem that I started with, which were these intriguing numerical observations. So if you restrict a power law XXZ chains, this relaxation rate is very simple. It's a square root of some quadratic equation. Of course, the coefficients are complicated, but at least as a function of delta, it's pretty simple. And the first feature of the numerics we need to explain is why the lifetime of the spin current had a unique maximum. So this is not a priori clear, but here it is as simple as solving a quadratic equation. So it falls out very simply from this formalism that there is a maximum delta as a function of alpha, and it is given by this ratio of infinite series. And this is precisely the physics that we were trying to model. I just computed averages of stuff at infinite temperature. So this was J dot squared over J squared, plug in XXZ, and do some calculus. And the crucial point is this is all quadratic optimization. Because I'm focusing on squared commutators, it's quadratic optimization, which is the easily solvable case of convex optimization. So that's really why this is so tractable. Other questions? Okay, so first, does this pass through the integrable points? Well, yes, as I discussed, because this automatically knows when J dot equals 0, it does pass through the Jourdain-Chastre and the XX points, which is nice. Second, does it match the numerical extrapolation that Mirzaevsky et al. Did? Well, actually, it matches pretty well. And in all its qualitative features, they were right. It's just quantitatively, we find a slightly different shape and a slightly different enhancement of the lifetime. So instead of e to the minus alpha, we have 2 to the minus alpha, but I think this would probably be within experimental error bars, say. I will say that our result is probably the correct one because we are looking at these short timescales where the Kubo correlation function explicitly just has this e to the minus t squared form at very short times. The reason there's no linear piece in here is actually because we're at infinite temperature and this correlation function is even in time. So this is the only accessible timescale in the problem in the large alpha regime, and therefore this analysis has to be giving the correct relaxation rate. So I think this solves the problem we set out to solve. And then the question is, okay, so how much further can we go? So we can get an effective relaxation rate from this too. The headline claim of their paper was that they had this relaxation time of 100 to 1,000 in their chosen units. And this is exactly what we find as well. So for generic points in this plot, this lifetime is very long. And as I mentioned before, this is probably the correct timescale that you're going to see. And the inset here is showing that we really only have a constant factor improvement over their results. So we get maybe 3 times the lifetime that they did, but the essential physics is the same. So I think there are some lessons here. First, elementary arguments can sometimes capture non-trivial physics in strongly interacting systems. Conventional transport theories don't seem to work here, but it would be a very nice test bed for them because I have an intuition that quasi-ballistic regimes are where collisions are weak. So if the collision integral is weak, there should be some collisionless kinetic theory nearby, but I'm just not sure what that is in this case. And so that's what we're really pursuing for these fermion problems, is trying to find that kinetic theory. Okay, so in my remaining time, let me just talk about some of these more rigorous investigations that we did for fun. So you can return to this space of generic inversion symmetric XXZ Hamiltonians. And one thing we were worrying about is, was it possible that Mirzaevsky et al. Were near a new integrable model that no one knew about, and maybe we'd somehow missed? So we investigated whether the spin current could ever be exactly conserved in the space of models, maybe for some model that we didn't know about. And you can show that a vanishing spin current implies this discrete functional equation. And it took us a while, but eventually we were able to solve it with minimal assumptions. And you can show that the only solutions to this vanishing current rate of change condition are just decoupled copies of XX models or decoupled copies of Jourdain-Shastry models. And the way the proof ends up telling you quite nicely all the different isomorphisms of XX and Jourdain-Shastry that are allowed, but it's only those. And I would say this is a baby version of an integrability transport theorem. So it was noted by Zotos, Naev, and Perlovsek a while ago that integrable systems seem to generically have ballistic transport, but the converse statement was never proved that ballistic transport implies integrability in lattice models. It's a conjecture that I think most people believe, and I think this is a baby step towards actually proving that conjecture, because at least for these models, we can show that an exactly conserved spin current implies integrability. I also wanted to rule out a Mazur bound. This seemed trickier, especially given that even for nearest neighbor XXZ, conclusively finding this quasi-local charge was a remarkable achievement. So we do expect this to be hard. We're going to try something much more modest, which is rule out two-body conserved charges. So if you look for a two-body charge that has the same symmetries as the spin current and would therefore overlap with it, you get now a functional equation for the charge, K, depending on the model couplings. But this is a linear equation, and just by doing some linear algebra, so you write multiple copies of these equations and take determinants, you can eliminate K and get a condition on the couplings alone to have this kind of conserved charge. So it's a cubic equation on the couplings, which tells you whether the model can have an odd parity two-body charge or not. And for the power law XXE model of interest, we can rule out such charges within this entire generic regime studied by Mierzejewski and co. So we would have to carry this out for many body operators with quasi-local tails to genuinely prove an integrability transport theorem in this case. This seems very hard, but it's more a question of being arduous than being impossible, because I don't see any obstacle to continuing this reasoning to higher body charges, say. And so there has been some recent literature on ruling out local conserved charges in, say, nearest neighbor or next nearest neighbor XXZ chains. But I think to say something about transport that is relevant to experiments, we really need to rule out quasi-local charges, which seems much harder. Okay, so I was very quick, but thank you for listening. And to my collaborators, I particularly want to flag the first author here, Jeb Song, because he was finishing his 4th year of undergraduate when I gave him this problem, and within 7 months we had a paper, so watch out for Jeb. And with that, thank you for listening.
Okay, thank you. Any questions?
Yeah.
Have you looked at this Izometsev chain?
That one, I think, will have KPZ.
And because there is also recently a kind of Q-deformed version of it, which introduced anisotropy to it. And
yeah, and so that version also looked very complicated because you need these many-body dressing tails.
No, but it's a possible candidate that would explain at least part of the physics that you observe.
I think so, but it's also making that connections is beyond reach.
Yeah.
So if you do this calculation at finite temperature, if you had taken the trace at e to the power of minus beta h state, so in that case, would the optimization give the same?
I can't do the calculation analytically at finite temperature, but I believe that in some window, if you do it numerically, I'm sure it leads to similar conclusions. Maybe with a different optimal delta and so on.
Okay, other questions?
Because the relaxation rate is a function of temperatures.
Okay, but so if I understand well, you have, I mean, with this maximization of the energy of the current variance, you get this argument to show that there at least there should be like long time ballistic transport. I mean, of course, we don't know if this continue forever, right?
Sorry, what's the question?
I mean, I'm just trying to summarize the result. I mean,
yes.
The question if the ballistic transport keeps going on forever is still on, right?
Exactly.
Okay.
So that's the question. And of course, if you're a reasonable physicist, you think, no, that's ridiculous. It's a lattice model. No. But to prove it, you would have to prove the non-existence of quasi-local charges.
And the existence of a kinetic theory, I mean, the question is, what are the quasi-particles of this model? It's not clear, right?
Exactly. So that's why I think correlation functions are maybe a more natural language than trying to, again, if we knew that they were, say, inner Zemtsev quasi-particles, that would be amazing. But I think our theory is just not in good enough shape.
Maybe have a question. So has anyone looked at what happens with the energy transport? Because in that case, then like XXC will have conserve. And so what is the structure of the energy transport in these models?
No, it's a good question. So I think again at these integrable limits, it's exactly conserved.
That's right, but also in the XXC. So also for delta non-zero and local will be conserved.
True. So then you probably have an even more quasi-ballistic energy transport. Yeah, it's a good.
But that hasn't been explained.
No, we have not.
Other questions?
This one.
Okay.
You started with with a question you asked about 2D Hubbard model, how your work relates to this.
Well, that was a long-lived ballistic mode is our best guess of what's going on there as well. And so the question would be, can we come up with a common theoretical framework for the long-lived ballistic modes in 1D and in 2D? But this is several years in now, and we'll see.
Any other questions? Not the case. Let's thank Vir again.